In this video, I want to introduce you to the curse of unrolling, a counterintuitive phenomenon observed when we unroll differentiate through an iterative algorithm. In this particular video, we want to approximate a quadratic convex optimization problem with a gradient descent algorithm. This will be very hands-on in JAX, so we will first look at the objective function and then assess the primal suboptimality, like how the optimization problem converges. Ultimately, we will find out that the unrolled Jacobian converges very strangely, and then we're going to explain this result with this simple example. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video. Automatic differentiation is a handy tool to take derivatives of almost arbitrary computer programs. And that can be a lot of things. For instance, in numerical computing or machine learning, that can also involve an iterative process. So for instance, the iterative solution to a linear system, the iterative solution to a nonlinear system, or the iterative solution to an optimization problem. Whenever you encounter these iterative procedures, you typically have two approaches to differentiate through them. Either you do unrolled differentiation or implicit differentiation. Implicit differentiation requires you to define custom propagation rules on how to differentiate these procedures, whereas unrolled differentiation unrolls whatever operations take place within the iterative procedure and differentiates them. This is what we are interested in this video. However, when you do unrolled differentiation, you can incur a very interesting phenomenon that's called the curse of unrolling, which in a nutshell basically means that the automatic differentiation does something weird which you would not expect to happen, or at least not intuitively. So for this, we will look at a very simple problem in which we have an optimization problem for a quadratic convex optimization. And we will also make it simple in that this optimization problem is scalar valued. So we have this optimization problem defined in terms of x and given by this quadratic objective 1/2 theta x squared minus bx. And this objective shall be parameterized by theta. So the theta is the scaling in front of the quadratic term. And then basically when we solve this optimization problem, we have an implicit mapping between the theta value and the arc optimizer of that problem. And this is essentially the routine or the part in your computer program that you want to differentiate. So you have some sort of a subtask mapping theta to x by solving the optimization problem. And now we do unrolled differentiation. And whenever we do unrolled differentiation, we need to open the black box and need to actually have our algorithm that solves the optimization problem being implemented in a differentiable way. Here we will consider a very simple gradient descent algorithm with a constant learning rate. So we basically say we approximate this solution, so we don't get the full x star. So we say this is something like an approximation after t steps. And we do so by performing gradient descent updates. So we start at initial condition and then we basically update it by going into the opposite gradient direction with an discounting scalar here. Since this is a scalar optimization problem, this will be very simple to implement. And now what we are interested in is the derivative of the output, so this xt, with respect to the input, with respect to theta. So in a more general case, when both x and theta are vectors, that is a Jacobian matrix. Here it will just be a scalar derivative, but think of it as a matrix. And then we are interested in this matrix suboptimality. So basically, how fast does that converge? And is it different from how the primal converges? This is what we were going to look at in this video. This notebook is inspired by a paper from NURBS 2022 titled The Curse of Unrolling, Rate of Differentiation Through Optimization. I like this paper a lot. Of course, in their paper, they discuss way more things than this very simple example that I'm going to show you here. For instance, they also discuss algorithms that have better properties in overcoming the curse of unrolling and more theoretical guarantees, but I hope this notebook will at least give you a good intuition. So let's get started with the coding part. Let me go down. I already imported JAX and Matplotlib and set the plotting style to a dark background. Then let's start by first defining this b value, because this is the scaling of the linear term. Let me set it to 0 for now. And then we can implement the inner objective. So this is basically the convex quadratic part that we solve as our inner problem. So let's call this the inner objective. And this shall take x and theta. And then it basically returns 0.5 times theta times x squared minus b value, which it captures from the environment, multiplied with x. We can analytically solve this optimization problem. It's very straightforward. And let's call a function that computes the optimum or the arc optimum by saying def inner objective arc optimum, which only takes theta now, and then it returns b value divided by theta. So let me scroll down. Then let's create a plot of what this inner objective looks like. For this, I will quickly paste in plotting. So basically, we will choose a range of x values, and then we have 4 different theta values, 0.1, 0.5, 1.0, and 2.0. There we evaluate the inner objective on the entire x values. And then we will also plot them. Ultimately, we will also plot the inner objective as a vertical line. And then basically what you see here is that in x we have our x value, and then here we have the loss, you can call it. So you see this is a quadratic optimization problem given by this quadratic function. And all the 4 different theta values indicated by the different colors have their arc optimum at 0. And the difference you notice in the theta value is kind of like how the parabola is shaped. In the case of quadratic optimization problems, you call this also the conditioning. So here, for instance, for theta 2, we have a steeper decline, whereas for theta being 0.1, it's a smaller slope. I will also show you how that basically is affected by changing this b value. Let's, for instance, set it to 0.01. And then you basically notice, or maybe we can also set it to 0.1. And then what you see is that we shift the analytical optimum. So now all of the 4 have different optima. And basically we see, for instance, for this turquoise color that the optimum is now at around 1.0. But let's keep the b value at 0 for now, so that all of them have the same value. Okay, now we are interested in the approximate solution of that optimization problem. So let's say, for instance, we start our optimization at 1.0 and let's fix theta to 2.0. Then the gradient descent algorithm will slowly go towards this minimum. It will reach it in the limit case, and we want to implement an algorithm that kind of produces the iterates of given an arbitrary starting point all the way to a certain point after a couple number of iterations. For this, let us implement the gradient descent step. So let's call this GD step, and this gradient descent takes basically an x previous, a theta, and a learning rate. And then it essentially computes an x next by saying that this is x previous minus the learning rate multiplied with the gradient. And how do we get the gradient? So here we will also leverage the automatic differentiation engine in the inner problem. So we will say jax.gradient on the inner objective, and then we will say argnums 0, which basically means derive the inner objective with respect to the 0th argument. And the 0th argument was x. So we will take the derivative of loss with respect to x. And then automatic differentiation in Jax is a function transformation. So we basically get back a function which we have to evaluate at its primal arguments. And this is x previous and theta. And then this gradient descent step returns x next. And now a gradient descent optimization is the iterative procedure we are interested in. So it starts at a certain point and then repeatedly applies the gradient descent step for a specific number of iterations, or until we reach a specific threshold. Here we want to fix the number of iterations. Let me paste in a function that does exactly that, but a bit more optimized. So let's call this optimize gradient descent. And then this takes a theta value and then a couple of values we already set defaults to. So we need an initial point. Here in our case, we have a scalar optimization problem. So this can be a scalar. We define the learning rate and we define the number of iterations we do. And here I'm using a very handy function, jaxlex_scan, which essentially performs the iterative for loop for us and stacks all the iterates. So essentially it produces a history of iterates. If we start at 0.5, where are we in the next step, in the step thereafter, and all the way until 1,000 steps. And I will also add the initial value to it. If you are more interested in using JAX-Lex scan, I have a video linked up here on its introduction in the case of autoregressive rollout. Okay, let's shift enter that function, and now we have this at hand. Let's fix a theta value and say theta shall be 0.05, and then we can use optimize gradient descent to produce a history of iterates. So let's say gradient descent iterates is optimize gradient descent on theta. Let's take a look at this array. So here we get our array. We start at 0.5. That's the initial point or the initial start for the optimization. Then in the next step, we are at 0.4975 and so on and so forth. And we reduce it and we go down to almost 3 digits after the comma. Still not fully 0, which would be the analytical optimizer, but it's already quite a progress made. Let's also take a look at its shape. So gditerates.shape. We see it's a 1001 dimensional vector because we not only performed 1000 steps, but we also concatenated the initial condition to it. With the iterates, we can compute the solution suboptimality. Suboptimality in that sense means how far we are away from the optimal point. Since we're here in this quadratic convex optimization problem, and also in the scalar case, we have access to the analytical optimizer, and so we basically can measure the distance we are away from this analytical optimizer. For this we will say jnp.absolute for taking the absolute value of the GD iterates minus the inner objective arc optimum, and we plug in theta. So this basically produces the scalar optimum value, and then we have an element-wise subtraction from the iterates and take the element-wise absolute. We can also compute the loss suboptimality. So here in that case, we have access to, again, to the analytical optimizer, and we can also see the difference there is in the loss. So we can basically say jnp.absolute of the inner objective evaluated at the solution suboptimality together with the fixed theta value, and then we subtract the inner objective evaluated at the inner objective arc maximum or optimum at theta together with theta. And now we basically have two 1001 dimensional vectors that we can plot. So let's do plt.plot on the solution suboptimality and attach the label, well, solution suboptimality. Then let's scroll down a bit and also add a plot of the loss suboptimality and attach the label of loss suboptimality. Then let's switch to a logarithmic y-scale because we are assessing a convergence. Typically this is with having the y-scale logarithmic. Then let's attach a label to the x-axis, which shall be the optimization iteration, and a y label, which is the suboptimality, so an assessment of the convergence of the problem, and activate the legend as well as the grid. So here we go. Let's first look at the solution suboptimality. So in the beginning, our initial solution suboptimality is somewhere between 0.1 and 1.0, and that makes sense because the initial value that we start our optimization with is 0.5. And the analytical optimizer, if we set theta to a specific value, I mean here it actually does not matter which value of theta we choose, because if we select the b of 0, then the optimizer will always be 0, because then we have 0 divided by theta. So essentially in the beginning we are 0.5 away from the analytical optimum. And this basically then goes down, and we see here a linear curve or a linear straight line, and this basically means we have an exponentially linear convergence. This is something we expect for the gradient descent applied to convex quadratic optimization problems. You can change the slope of that curve by choosing, for instance, a better learning rate, but at least we will always have a linear curve. And then of course in the limit, after more than 1000 steps, we will at some point reach machine precision. So here by default in JAX, we are working in single precision floats. So the machine precision is somewhere around 10 to the minus 6. And then we will notice a full convergence, so there will be no further improvement. But here with this particular setting, we will not notice that. Arguably, of course, the setting we chose here is a bit suboptimal for perfectly solving this optimization problem. Let's now finally come to the unrolled differentiation, because so far we've only solved the optimization problem in the forward pass, but now we are interested in taking the derivative. So let's take a closer look at what actually happens here. So the function optimize gradient descent is a mapping, so if we ignore the other arguments, is a mapping from one scalar value to a 1001 dimensional vector. So essentially it not only contains one approximate solution to the optimization problem, but the first 1001 of the gradient descent procedure. And that's very helpful because this allowed us to plot the convergence. Now we want to take a derivative of all the 1001 iterates with respect to the input theta. So we have a mapping from 1 to 1001, and now want to derive all the 1001 with respect to theta. In general, of course, when you do automatic differentiation, especially in the context of machine learning, you would do reverse mode automatic differentiation. For instance, in neural network training, you have a lot of parameters and a scalar loss. So high dimensional mapping to a scalar or to a small dimensional space, perfect for reverse mode. But here we have a mapping from 1 to 1001, so very small input space and certainly large output space. So here it's reasonable to use forward mode automatic differentiation. This does not affect the curse of unrolling. Forward mode and reverse mode automatic differentiation in infinite precision produce the same gradient estimates. It's just the way how they perform the automatic differentiation. And here it's very smart to do forward mode. So we can compute the iterate Jacobian. So iterate Jacobian, which is Jac forward for a Jacobian computed with forward mode automatic differentiation on optimized gradient descent and argnums 0. Derive the procedure that produces or solves the optimization problem with respect to the 0th argument, so with respect to theta, and then evaluate it at the primal input theta. Let's take a look at its shape. So iterate Jacobian.shape here is also 1000 by 1. And I want to leave the important remark that if you do higher dimensional optimization problems, your iterate's shape will be 1001, the shape of the iterates. So for instance, if you have an optimization problem in a 50 dimensional space, this will be 50. And then the Jacobian will essentially be 1001, the shape of your iterates, which let's say is 50 again, and then the shape of theta, which could for instance be 30. So it will be number of iterates, shape of x, shape of theta. But here in this very special case where we have a scalar optimization problem and also theta is scalar, that will just be a vector. That's also more easy to work with. This is the iterative Jacobian or the unrolled Jacobian at each particular iteration. And then we can compute the exact Jacobian. And the exact Jacobian is by using an Jacobian. So here we can either do forward or reverse mode. Let's do also forward mode on the inner objective arc optimum. We don't have to define argnums because here this only has one argument and this is theta. So here in this very simple case, we have access to the analytical optimizer. And then of course we can also derive the analytical optimizer, which gives us the exact Jacobian. But of course, if we take a look at it, that here the inner objective is b value divided by theta, and we set b value to 0. And if we derive this with respect to theta, this will also be 0. But of course, in the more general case, if you augment the b value, then you will also get a corresponding Jacobian. Okay, then we can compute the Jacobian suboptimality. So Jacobian suboptimality. And this is given by computing the distance between the Jacobian at each iteration and the exact Jacobian. So we will use absolute again because we are in the scalar case. In a higher dimensional case, you will likely need to use a norm, typically the Frobenius norm with jnp.linealc.norm of iterate Jacobian minus exact Jacobian. Let's execute that. Then let me paste in a plotting command that plots the solution loss and Jacobian suboptimality next to each other. That's also what you already saw in the intro. We again see that the solution suboptimality starts at 0.5 and then has this linear convergence. And now we see the curse of unrolling in action, in that the Jacobian suboptimality does something very strange. So it initially starts at a very low value. It actually starts at 0. That's just a glitch of the initial condition we chose here. But imagine it started at a value here, let's say 10 to the minus 2 to 10 to the minus 1. And then it got worse. Put this into words. You see that your primal optimization makes progress. So you get closer to the optimization problem's analytical optimizer. But your Jacobian gets worse. And if you use that within an outer optimization problem, where you use the Jacobian to get a gradient for training a neural network, for instance, then you would see that the gradient estimate also gets worse. So it turns out that in the beginning, we see that Jacobian is very bad, actually. And then after some point, after some inflection point, it actually tends to get better again. And something you can barely see here, but I hope you can trust me on that, is that after a certain while, it will then take the same convergence rate as the solution suboptimality. So at a certain point, it will then also become a straight line. And of course, ultimately, we will also converge against the exact Jacobian. But we will have this very counterintuitive glitch up here. So what happened here? Is the automatic differentiation engine broken? Did checks do something wrong? Is that something we should expect? Let's take a look at what actually goes on. For this, let me paste in a markdown block and let's go over that. Again, let's recall that our inner objective was this quadratic convex one. And here I purposefully removed the linear term because we set b to 0. So we only have a half theta x squared. Let's look at the iterator that is part of the gradient descent algorithm, which says we do x minus eta times the gradient. We can derive the gradient analytically. So if you take the derivative of this function with respect to x, you get this is theta x. So we have x minus eta theta x. Then we can bracket and get 1 minus theta eta in brackets times x. And this is an iterator that we can apply autoregressively or repeatedly. And this is essentially what the scan function did. And the scan function, well, it applied it and then stacked all the iterates. But here we get that the iterate at iteration t is basically phi t times the iterator applied to the initial condition. So 1 minus eta theta to the t. And this is basically the iterates we get. From this, we can also derive that the convergence of the primal is exponentially linear because the t is in the exponent. So we have a t in the exponent, meaning that we see this convergence exponentially linear, so meaning that it is linear in a log plot. However, if we now take the derivative of the iterate with respect to theta, we see that what we ever take the derivative with respect to is in this bracket raised to the t. And so deriving this with respect to theta essentially gives us, first, the exponent comes down and we get the outer derivative, and the inner derivative is minus eta. And now we have an exponential term and a linear term. And the linear term is the one that makes the problems. Let's take a look further at our problem. The analytical optimizer can be found to be 0 in that particular case. And as such, what we also saw earlier, the analytical Jacobian is 0. If we now take a look at the Jacobian suboptimality, so subtracting from this the optimizer and then taking the norm, which in the scalar case is just the absolute, we see essentially, if we plug in our concrete values, that we have a linear term and then we have an exponential term. And they kind of work against each other. And let's take a look at what their concrete effects are by a small plot. So let's implement a t range. So here I want to set the number of iterations basically that we want to consider, and let's have a little bit less than what we had in the beginning. So let's have jnp.arrange from 1 to 500 instead of 1000. And then we compute the linear sequence, which is 0.05 times t range. So this is essentially that part here. And then let's also compute the exponential sequence, which is 0.995 multiplied, or sorry, not multiplied, but raised, so double asterisk, to t range minus 1. Let's execute that. And let me paste in a plotting command that produces, I think I spelled something wrong, so there should be a U. Now it works. So essentially we get a plotting of 3 different sequences. For now, let's only look at the linear and the exponential sequence. So the linear sequence, as you expect, it's positive, so it linearly raises up, so starts at a low value and then gets greater. Then we have the exponential sequence. This one is decaying. So here you don't see that it's actually exponentially decaying, but because we just look at a small snapshot here. However, if you now look at the product of those, you see that the product initially increases because in the beginning, the linear term is dominant. However, if we look at a longer range, so let's plot the product only over the 500, and then we see that in the beginning for these first 30, so until here, the linear term was dominant, and it still keeps to be dominant until this inflection point. And then this point, the exponential term actually kicks in and is way stronger and ultimately causes the linear decay we see. So here it is still a bit of a snapshot, so we also have a linear axis on the y-axis. But if you continued that beyond the 500 and then switch to a logarithmic scale, you will ultimately notice that we get the exponentially linear convergence. And you will notice that this inflection point is around at 200, so it's actually exactly at 200. And let me paste in another explanation block. And we see that this burn-in phase, that's also how they call it in the paper, is proportional to 1 over kappa, and kappa is the conditioning of the optimization problem, which is just here defined by theta to be 0.05, and inverting that is 200. So we get the inflection at the 200th iteration. And of course there is way more to the curse of unrolling. I want to paste in another explanation block, and basically this means I want to encourage you to play around with this notebook, so you can download it from the link in the video description, and for instance change the learning rate. You can change the linear term in the objective, the initializer, and so on and so forth, and you will see that all of them somehow affect the curse of unrolling, some more, some less, and you will ultimately see that the curse of unrolling is described or can be described by the following statement, in that they say, to ensure convergence of the Jacobian with gradient descent, we must either 1. Accept that the algorithm has a burn-in period proportional to the condition number, so this is what we saw, or choose a small step size that will slow down the algorithm's asymptotic convergence. So this basically means we have to kind of decide between either we want to have the curse of unrolling or this particular counterintuitive phenomenon happening that our Jacobian gets worse, or we have to greatly slow down the overall algorithm's convergence. In another perspective, this would also slow down the primal convergence. So we need to make a balance between that, and since we cannot have both optimal or perfect, this is called the curse of unrolling. And I would encourage you to check out their paper for more details on the theoretical analysis and particular algorithms that have better unrolling properties. Also check out next week's video where we will compare the unrolled differentiation with the implicit differentiation approach. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more content on automatic differentiation that you're probably interested in. Here you will now find similar videos, and I hope to see you in one of the next videos.